All right, welcome to The Explainer. We talk a lot about the theory of quantum computing, but today we're getting our hands dirty. We're going to move from theory to practice and actually write the code to fight back against quantum errors. This is going to be a step-by-step guide, so let's jump right in.
So, here's the game plan. First, we've got to understand the enemy, quantum noise. Why are these machines so finicky? Then, we'll code up our very first circuit. After that, we'll throw it into a realistic, noisy simulation and, well, let's just say we expect things to go wrong. And that's the best part. We'll then code the solution and see if we can actually save the day.
Okay, let's dive in. First things first, we need to wrap our heads around the big problem here. You can't fix something if you don't know why it's broken, right? And this is a challenge that every single quantum computer, no matter how advanced, has to deal with.
It's kind of funny, isn't it? The very thing that makes a quantum computer so powerful is also what makes it so fragile. It's this beautiful paradox. A qubit's ability to be in superposition, to be a 0 and a 1 at the same time, that's the source of all its magic. But that delicate state, man, it's so easily disturbed. The slightest little vibration or temperature change can mess everything up.
And that disturbance, that's what we call quantum noise. The best analogy I can think of is like static on an old radio station. You're trying to listen to the music, that's your calculation, but all this unwanted interference just corrupts the signal. It introduces errors and messes up your final result. Honestly, it's the #1 enemy we're fighting in this field.
And it's not just one thing causing the trouble. It's a whole gang of culprits. You've got stuff like thermal relaxation. That's basically the qubit just getting tired and falling from a 1 back down to a 0. Then you've got dephasing, where it loses its rhythm, kind of like a spinning top that starts to wobble. And it gets worse. The very tools we use, the quantum gates, they're not 100% perfect. Even the simple act of looking at the result can introduce errors. It really is a battle on all fronts.
All right, enough talk about the problem. Let's start building the solution. It's time to write some code. We're going to build a simple quantum program from scratch using a fantastic Python library called Qiskit. If you're into quantum coding, you've definitely heard of it.
And you know what? It's actually not as complicated as you might think. It really comes down to just 3 basic steps. First, we initialize our quantum and classical bits. Get our workspace ready. Second, we add the gates that form the logic of our program. And finally, we'll draw a little picture of it just to see what we've built.
Okay, step 1, setting things up. We just import quantum circuit from the Qiskit library. And then this line of code right here, it's super simple. We're just creating a new circuit and telling it, hey, I'm going to need 3 qubits to do the quantum stuff and 1 classical bit to write down the final answer. Think of the qubits as your calculators and the classical bit as your piece of paper. All right, now for the fun part, adding the actual quantum logic. That first bit of code, qc.h of 0, that's the Hadamard gate. This is where the magic starts. It puts our first qubit into that weird state of being both a 0 and a 1 at the same time. Then, you see those C0 gates? Those are C0 gates, and they do something mind-blowing. They entangle the other 2 qubits to the first one. Now they're all linked. What happens to one instantly affects the others. We've just created what's called a GHZ state.
And of course, what's the point of doing all this if we can't get an answer? So this last line, qc.measure, is pretty straightforward. It just tells the computer, okay, time's up. Look at that first qubit, figure out if it's a 0, 1, and write the result in that classical bit we saved. And believe it or not, that's it. We've written a quantum program.
Now, before we hit run, it's always a good idea to see what we've built, and that's what qc.draw is for. It spits out this awesome little diagram. You can trace the path of the qubits from left to right, see the Hadamard gate, the 2 C0s, and the final measurement. It's beautiful, right? This is our circuit in its perfect theoretical form.
So yeah, it looks perfect on the screen. But that's the on-paper version. Now comes the real test. What happens when our perfect little circuit has to face the messy, noisy reality of the real world?
And really, this is the million-dollar question, isn't it? This is where theory crashes into practice. An amazing algorithm is totally useless if it can't survive the trip through a piece of real, imperfect, noisy hardware.
So how do we find out? We don't even need a real quantum computer for this part. We can use Qiskit's built-in simulator. And what we're doing with this code is creating a noise model. It's like we're telling the simulator, hey, I don't want you to be perfect. I want you to act like a real, slightly janky quantum computer. Give every gate about a 5% chance of messing up. This is a great way to mimic what happens on actual hardware.
And here we go. Ugh, yeah, that's not good. See, in a perfect world, this circuit should always give us a 0, 100% of the time.
But look at this chart. We're getting the right answer most of the time, sure, but there's a pretty big bar there for the wrong answer, 1. The noise completely corrupted our calculation. Our beautiful, perfect little program just got wrecked by a dose of reality.
But are we just going to sit here and take it? No way! This is where things get really cool. We're not just going to run it again and hope for the best. We're going to go back into our code and build a defense system. We're going to fight back against this noise in real time. So here's the strategy. The goal is simple. Protect that fragile quantum state. And the tool we're going to use is super clever. The idea is to not wait until the end to see if something went wrong. We're going to check for errors in the middle of the calculation. And if we find one, we'll use a simple if-then statement to fix it on the fly.
This amazing ability is called dynamic circuits. And trust me, this is an absolute game changer. It means our quantum circuit isn't just blindly following instructions anymore. It can measure something, think about the result, and then change what it does next. It's real-time decision-making, and it's the secret sauce for all serious quantum error correction.
And here it is. This is the code that does all the heavy lifting. It's so elegant. First, we measure a qubit, just like before. But then we have this if-test block. That's basically a classical if statement hiding inside our quantum circuit. It says, hey, look at the result of that measurement. Did you get a 1? Because that 1 means there's an error. And if the answer is yes, boom, it instantly applies an X gate to flip that qubit right back to 0. It detects the error and fixes it just like that.
Okay, the fix is in the code. We've run the whole gauntlet. We built the circuit, we watched it fail, and we wrote our correction algorithm. So, did it work? This is the moment of truth. Let's run that noisy simulation again and see what we get.
Whoa, look at that. Yes, it worked. Just look at that chart. Remember the last one with that big, ugly bar for the wrong answer? It's practically gone. It's just a tiny little sliver now. We did it. We used a few lines of code to actively suppress the noise and protect our result. That's awesome. This picture really tells the whole story, doesn't it? Imagine that orange, spread-out curve is our noisy, error-filled result. It's all over the place. And what our code did was act like a shepherd, herding all those scattered results back towards where they belong, creating that tight, accurate blue curve. That's not just a graph, that's a picture of what your code can do.
So, let's just take a breath and think about what we just did. In just a few minutes, we went on a complete journey. We started with this big, scary problem called quantum noise. We built a quantum program from scratch in Python. We saw that program fail under realistic conditions. And then, the coolest part, we used a dynamic circuit to actively correct the errors and got a much, much better answer. From problem to solution, all in code.
And that leaves us with one final, huge thought. Look, what we did today was fix one type of error on one qubit. It's a small step, but the principle behind it, this idea of dynamically detecting and correcting errors, that's not a small step. That is the fundamental building block for the holy grail of this entire field, a fully fault-tolerant quantum computer. The challenge ahead isn't about figuring out if this is possible anymore. We know it is. The real question is, how do we take this exact idea and scale it up to protect thousands or even millions of qubits all working together?